Welcome to Physics 246 Online. Today I'm going to give an overview of the topic of error propagation that comes from Chapter 3 in Bevington's book. Error propagation is really the answer to the question, what is the uncertainty in a result that's computed from measured quantities, each of which has its own uncertainty? A couple of reminders here. The word uncertainty is basically synonymous with the word error in the context of this subject. Also, this video is not intended to be a substitute for reading Chapter 3 in Bevington, but just to give an overview of one major part of that chapter. So as you watch this video, or after you watch this video, please also read the chapter and, of course, take the reading quiz. So this comes from section 3.2, and as I already alluded to, suppose in an experiment you measure various quantities. U and V are the symbols that we'll use for these quantities, but there could be more than two, and these quantities are used to compute the result that we're really interested in, x. So in this way, x is a function of the measured quantities U and V and W and however many others that we have. So if we do repeated measurements 1 through n for these quantities U and V, we would end up with individual measurements of the quantity we're really interested in, x. The x values are not all the same, of course, due to fluctuations in the measured values of U and V. So we have two questions. First of all, what's the best representative value for the final answer x? And what we're really asking for is in the distribution of all possible values of x, what would be the best value for x coming from that parent distribution. We've already talked about how this is the mean value. We haven't proven that or justified that yet, and we'll return to that topic in Chapter 4 to show that the best estimate of the true x value from the parent distribution is the mean value. So we've seen this before. The second question is a little bit more difficult. What is the uncertainty in the result x? So the uncertainty in x is the square root of the variance, sigma x squared, and we call that the standard deviation. So we could calculate that from individual values of x obtained through these n different trials in which we were actually not measuring x directly, but we're measuring the quantities u and v. And we're actually going to use this in order to calculate an expression that's a little bit easier to work with for this variance. Remember that xi minus x bar, right, is the term we use for this is the deviation of the measurement x sub I from the mean value x bar. So we're going to make three assumptions as we use that definition to come up with an estimate for sigma x squared. We're going to assume that the deviations in x are due to random deviations in u and v about their mean values. Secondly, we're going to assume that in general, if you do the measurements of u and v and then come up with mean values for u and v from your n measurements, that the mean value of x is given by whatever the function is, which contains u and v. And that's not necessarily an obvious, it's very intuitive that that might be true. It's not so obvious, but it turns out in the limit of a large number of measurements that that actually is true, that the mean value of x, of all possible values of x, is given by whatever the expression is that shows how u and v are related to x, evaluated when u and v are at their mean values. And then the third assumption is that the deviations about the mean for x, u, and v are all small. And we're going to use a Taylor series approximation for this quantity xi minus x, and we will then use the Taylor series expression and make a good approximation, if these deviations are all small, that we can just keep the first order terms. So in principle, a Taylor series is an infinite series, but in many cases you can keep just a few terms if you know that some of the quantities in the Taylor series are small. All right, so how does this work? Here's the Taylor series. Remember that we've measured lots of different trials of u and v, and we're interested in finding x. So there's some function, maybe, just to give a specific example, maybe we're trying to measure the volume of a cube, right? And U and V and perhaps W are the length, width, and height, or maybe not a cube, that's a bad example, but something that's a rectangular solid, where the sides are not necessarily all equal. So if U and V and perhaps W represent the length, width, and height of the cube, then we would be multiplying them all together in order to get the volume. So that's one example. So here the Taylor series expansion would be written like this: that the deviation of individual value of x from the mean is equal to the deviation of u from the mean times this partial derivative of x with respect to u. And we'll have a similar term for v, and then we'll have the second order terms, which will include this deviation quantity squared and the second partial derivative, and so on and so forth. So we won't write those all out right now, but just show you where we're going. So one note about partial derivatives is that the value of that partial derivative is taken with the other variables that are not involved in the derivative at their mean values. So if you're not real familiar with partial derivatives or you haven't used them in a while, don't worry, I will go over those in class. So now we're going to take this expression, this Taylor series expansion, which is only exact in the limit of an infinite number of terms, and we're going to substitute that into the expression for the variance in x. So we will take that expansion and plug it in here in the summation of all values from 1 to n. So what that gives us, just simply making the substitution, looks like this. But remember, this term in brackets is squared. And so when we evaluate this, we're going to get the square of each individual term, plus we will get cross terms that come about from the products of the individual terms that are inside this bracket. So it's going to get very complicated. So there, that's just rewriting what I had on the previous slide. And now we will write down the first three terms that arise. Basically, the first term squared, right? The second term squared, and then twice the cross term, which we know is what happens if we were to multiply out by hand these terms in brackets. So we get this cross term that has 2 times the product of the deviation of u, the deviation of v, and the product of their individual partial derivatives, the derivative of x with respect to u and v. Now, when we do the summation of these terms individually, because remember, if you have the summation of a bunch of terms added together, that's the same thing as the sum of each of the terms added together. So what we will do is first evaluate the sum of the first term and the second term. And those turn out to be very easily evaluated because we already know that the variance in u and the variance in v has this form. And I'll just flip back for 1 second. Note that that's what the first term contains along with this partial derivative. And the partial derivative does not depend on the individual measurement, right? That is obtained from the expression for x as it depends on u. So that term is not something that is actually inside the summation. It can be taken outside the summation. And the same thing is true with the second term for v. So then what that does, the first 2 terms are written like this, where the variance in u squared, right, times this square of this partial derivative, plus the variance in v squared times the square of this partial derivative, get written out like this. The third term, which is the cross term, we're going to make a definition and write it in a more compact form like this. So I'll flip back for a second. You'll see that it does include the product of these partial derivatives. And then what we're going to do with this term here, the sum over all the individual trials n of this term here, is we're going to give it a special name, and we will call it the covariance. So the 2 remains out here. The dx du and dx dv terms are here, and everything else that represents that summation is in this covariance term. So the last term includes this definition. So it's not something we've seen before, but it's something that if we knew all of the values of u and v and we knew all the mean values, we could easily evaluate. It's called a covariance because it includes the variance of u and the variance of v taken together and multiplied. And we'll talk in a little bit about how or what kind of a value this term might have. Do we expect it to be a large value or perhaps a small value? So this gives us the general error propagation equation. Remember, we've just written out the first order terms, right? So there are going to be higher order terms as well, which will include things like higher powers of these derivatives, and then products of higher powers of those derivatives as well. But here's one of our assumptions comes into play. If we assume that these variances are small, then the higher order terms will include higher powers of those variances. And so if the first order terms are small, then the higher order terms will generally be even smaller. So if we make that approximation about the size of those variances, quite often we can approximate the overall expression for the error or the variance here in x by stopping the summation after these three terms. All right, now let's go back to that covariance term. If u and v are independent of one another, so in other words, if we measure u and we measure v completely independently so that their values don't in any way depend on one another, then you would expect that u sub I, any individual measurement of u, is just as likely to be positive, or is just as likely to be higher than the mean as it is to be lower than the mean. So the first term in the summation could just as easily be positive or negative, and the same thing is true of the second term. So if we only had 3 trials, then we wouldn't be able to make any kind of useful approximation or assumption about the result of this. But if n is a large number, then we'll be summing up quantities multiplied together that are just as likely to be positive as they are to be negative. So in the limit where n is large, as long as u and v are quantities that are independent of one another, they don't depend on one another through any kind of a functional form, then this expression will often be very close to 0. And so that leads to a simplified version of the error propagation equation, which is equation 314 in the textbook, where the covariance term has been dropped out. So as long as we have good reason to believe that u and v are independent of one another, and as long as we're working with a fairly large number of measurements, that is a good approximation to use. So in practice, this will be the starting point for working out how the errors in u and v propagate to give us the overall variance in x, and then of course the error in x. Applications, all right? Error propagation is simply applying these error propagation equations to the various functional forms in which the measured values of u and v combine to give us the result that we're interested in, which is x. The example I gave earlier was the volume of some kind of rectangular solid, and we'll do examples of this in class. So remember, even though in the textbook there are lots of examples that are given for various kinds of functional forms, don't memorize a host of individual equations. So it's not a good idea to try to memorize what the results are for various kinds of functional forms. Just remember equations 313 and 314. Those are the starting points that can be used for any general function. So how do we get sigma u and sigma v? Just a reminder, those will depend on how those quantities were measured. One way to do it is just to measure u and v many, many times to get large number of trials and find the standard deviation in those measurements. And then the error in the mean, which is what we'll talk about a little bit later in the course, is going to be the best estimate of the error in that particular value. So we can do it that way. Another way would be to take our distribution of the measurements for u and v and fit some kind of a distribution function to those individual measurements and extract the best value of sigma u or sigma v from the results of that fit. If the number of measurements is a large number of measurements, then this result should be the same as what we get by simply calculating the standard deviation. But in some cases, especially if we know that the distribution function is not a Gaussian function, then this might give us slightly different results. And then sometimes, particularly if we're only able to make a single measurement of u or v, we may just have to make an educated guess to assign the error, and that will often depend on the technique that we're using to do the measurement and the measuring instrument itself. Here's an example. I'll state the example and then work it out in class, but just to give you a very concrete, specific example. If you have a pendulum of a certain length, we know the error in the length, and it's displaced from the vertical position by a certain angle, where we understand the value and its error as well, we want to find the height of the pendulum measured from its lowest point. Okay, so at this particular angle, what's the height of the pendulum? Clearly, that height will depend on the length of the pendulum and the angle. If we make the angle larger, then this height is going to be larger. If the length of the pendulum is larger, the same thing holds true. So there's a simple function that relates L and theta to the height, and we will give the result after working out this example in class. So I hope this has been a helpful introduction to Chapter 3 in Bevington and Robinson's book, and I will see you in class.